on a second. Come here first. There you go. All yours.
Great works. Right, well, good morning, ladies and gentlemen. My name's Ali Bruce from the Bluebell S&T. My presentation is about our project to operate signals using hydraulics. So here's a site that's probably very familiar to most of you. It's a platform starter at Kingscote. Particularly interested in this little device here. It's called the Westinghouse signal machine. These lovely machines are nearly 100 years old now. They're a testament to the original design and build that we're still using them after all this time. But unfortunately we need to look into the future. We're worried about support, we're worried about spares, so we decided to look into replacement for the machines. Oops. The clicker stopped clicking.
Left and right.
Stop.
Can
you move me on, please? Oh, there we go. Right, I'm working it. Okay, so any new project, we've got to set down some design criteria. So we wanted something that was reliable, very important, we wanted something fail-safe. If we lost local power, the signal must return to on. For the Bluebell in particular, we have a long section in our middle station, Horse and Canes, where in a hub various signals can be off for days and days and days. So we wanted the signal arm to be able to be held off without any re-pumping for well over 5 days. We also wanted it to be based on anything that was free, as much as possible. We wanted it to be easy to maintain. With us being a heritage railway, we wanted something that's not too obtrusive. So, we chose hydraulic operation. There's various other methods we could choose, but we chose hydraulics because basically we knew that British Rail had already used them. We know that our good friends at the East Lancashire Railway developed hydraulic operations. They are years ahead of us, by the way, and they've been very helpful. Ultimately, we've gone down a slightly different route to them, but the East Lancashire have been very good to us, particularly in our original days. We also know that at the time we knew the Watercress were looking into these. We subsequently found that other heritage railways were all looking to hydraulic operation. Probably most importantly, clamp lock power packs, which are used to operate points. Our good friends at Network Rail, every now and again, dispose of them. And we say, can you dispose of them in our direction? So we've amassed a number of clamp lock power packs, and that's ultimately what we've based our design on. So moving on, let's look at a simple hydraulic circuit. We suck hydraulic oil out of a tank, through a pump, through a valve. We control the direction it's going in, and we squirt that up to an actuator. So an actuator, people call them rams, cylinders, call them what you want, but the actuator converts hydraulic flow of oil into mechanical motion. So if we want the signal to go up, we power the pump and place a direction control valve so it's pumping fuel to the actuator. If we want the signal to go down, or if there's a power cut, power failure, the direction control valve defaults to this position. So power failure, or the lever going back to normal, the weight of the signal arm will press the fluid back through the direction control valve back into the tank. That's a very simple circuit, and if it's as simple as that, I'd have been banging on here 5 years ago instead of now. Because one of the problems with the direction control valve is it's actually a little bit leaky. So if we pump a signal up using a direction control valve, which this electrical analogy of the valve is more like a changeover contact, we try and hold it on for an appreciable amount of time, that signal arm will slowly drop back and will leak into the tank. So that is a big problem. We decided to base our system on clamp locks, as I told you, so bearing in mind the problems we discovered with leaky valves, I'll discuss how the clamp locks work. So clamp lock here, you've got the lope full of the relays, you've got the power pack. In the forefoot, you've got two actuators. So as one's expanding to push the switch rail across, the other's compressing. And the clamp lock is always a two-way system, so we squirt fluid in one way and fluid goes back in the opposite direction. In between movements, there are little check valves which seal the fluid in. So the switch rail fits snugly against the stop rail, holding it in position. The clamps come round, hence the name clamp lock. But it's a two-way operation that gives us problems. We can't just simply stick a hose on it up to a signal because we pump it up and we have to pump it back down. And of course we want the fail-safe system. So we can't really use the clamp lock as it is without some sort of modification. So moving on. There's two ways we can modify this. One is actually very, very simple. We just remove a ball bearing from the check valve within the pump and you can pump the signal into the off position. That's the one that leaks because everything's being held now on the direction control valve, which is a leaky valve. In the clamp lock scenario, it doesn't matter because you've got the check valves holding the pressure in. So that's one option. Option two is to install a little valve called a Poppet valve, which is very, very leak proof, and ultimately that's what we use. But because the first modification is relatively simple, our running prototype, which we installed at a siding in Kingscote, we based on the original idea of just taking the ball bearing out. So here it is at Kingscote, right? The clamp lock power pack's there, the actuator is there. What you see around there is a standard circuit closer, a standard repeater box. And we actually use that to control the pump. So when we want the signal to go off, pull the lever back, we activate the direction control valve, we activate the pump, pumps the signal off. Then when we get off detection, we use the off detection from the standard repeater to stop the pump. So we don't have to festoon it with any extra contacts, this, that and the other. This gives us a problem that with this system, with a shunt signal, it will slowly leak off after about 20 minutes. Once it leaks off past that off detection, of course, it pumps back up again. So if we put that on an in-home signal, what would happen was the signal would be going, and then it back up. The outer home before that would be dancing up and down. The distance before that would be dancing up and down. So we wouldn't get a lot of street cred from the train crews. So ultimately, it's great for a shunt. It's great if you only want something to go off for a few minutes. It works a treat. It's also given our designer a lot of experience in the electrical design. So it hasn't been a waste of time. This has been in service 3 or 4 years now, perhaps, and it actually does work a treat. But ultimately, it's not the way to go for us. So let's move on. Let's think to stop. Here we go. I talked about a Poppet valve earlier on. Poppet valve is basically a tapered needle that will fit snugly into a tapered orifice. We are using normally open Poppet valves. Basically, the spring holds it open. So with the spring holding the valve open, without any power on the solenoid, fluid can flow in here and down here. So it's de-energized. De-energized keeps it open. If we want to close it, we energize the solenoid coil, and this forces it down over the spring pressure. The magnetic force forces it down over the spring pressure, and it closes it. And that little taper sticks snugly into the tapered air, and it's an excellent, excellent leak-free valve. So this is what we based our ultimate system on. I guess the electrical analogy for this valve is just an on-off switch as opposed to a changeover switch. So let's have a look at the inside of a clamp lock that we've modified. That black thing there's the motor. The pump is actually underneath. The Poppet valve itself consists of a valve block, a valve cartridge that's screwed in, and a coil that we energise to control it. The fluid flow will go in through this port here, and when the valve is de-energised, the flow can go through this port, and it drops straight down into the tank at the bottom. We put a little pipe in it, and the filter, we use the same filtering as a standard clamp lock. So that gets the fluid back. What would be here normally on a normal clamp lock is very large direction control valve, because we don't need that anymore because we've got the Poppet valve. So we've taken that off, discarded it. We replaced with this little block here, which is called a C-top crossover plate. C-top is the standard at these international hydraulic standard. But basically all it does, it takes the fluid from the pump and squirts it out through one of these ports. So basically, if I took the cover off that port, started the pump going, it just chucked fluid everywhere. Believe me, we've done it quite a few times. So we've also retained the hand pump, which is great. We can actually pump the thing up to set up circuit closers. We can pump it up to a very sort of precise angle and work out our setting up our circuit closers. So the next bit of the modification is we put a little T-piece there. So now the fluid can go in two different directions. If we want the signal to go off, basically we energise the valve and it closes it. So as we squirt fluid out of there, it can't go anywhere because that valve is closed. So it goes straight up the spout, up to the actuator, up to the signal. What we've also done is put a little flow restrictor in there because we needed to calm it down. It was all going up far too quickly. Put the flow restrictor in, it calms it down a little bit. If the signalman puts the lever back, or we have a power cut, we lose the power on that solenoid, the valve opens, and the pressure of the fluid being pressed down by our signal arm pushes the fluid back to the tank. So we've now got our fail-safe tick in the box. We've now got the electrical circuits coming there. That's just a little spacer which happens to fit perfectly on top of that block, and we can fit the standard mounting plate there. This little device here, there's a little hasp with a hole in it, so when we put the lid on, we can put the padlock through. In a home accordion signal at Horsey Canes, it's mounted on a gantry. It's deemed to be a little bit dangerous at the moment. Calling on the signal is also colour light subsidiary, not quite in keeping with the heritage look of the station. And the route indicator, again, is a great big square boxy thing, not quite in keeping. So we are making another signal to the left of the track where the original one always was, and we're going to have a traditional semaphore calling on. So we need two pumps, one for the inner home, one for the calling on. We're going to put the new route indicator up there. What we'll do, because we are still not there, I would dearly love to be here to tell you it's all working, but we're probably going to transition it early next year, January, February time. So all I can show you, unfortunately, is the signal in its construction phase. So we've got the two pumps here. What I did, we built two pumps, we've got two spares, and we're building another one that we can use for further development. This entire system, with it being within the station boundaries, works on 120 volts because that's the standard clamp lock voltage. We've got a development system that we're looking into where we're going to try and get the thing working off 12 volts. That's watch this space at the moment. So we have our two pumps here. This is our new signal. It's dressed up a little bit more since then, but unfortunately it's not quite in operation. Hopefully in a couple of months we'll transition it in. So that really comes to the end of my little presentation. So in true fashion, we've really got to do a few thank yous. Peter Duncan from the East Lancashire Railway, excellent. He's been such a great help to us in the early days. Ian and Mike, and the sponsors. Don't forget the sponsors, big thank you. Severn Valley Railway, Kidderminster Museum for letting us use this. And finally you lot for not heckling.